In this tutorial, we will be looking at how to set up a simple operational amplifier circuit, both with an ideal model and a real model. If you find that this tutorial is too fast or too difficult for you, please refer to the previous videos which were posted on Blackboard and YouTube. So first of all, we want to create a new circuit schematic. We go to Circuit Schematics on the Project tab, we right-click, select New Schematic, and we call it Ideal Inverting. Now we can simply get ourselves an ideal opamp. We press Ctrl L, and as you know, we can search by name or description by simply Ctrl-clicking on the heading that we are interested in. In this case, I know that the opamp is called Opamp, so I'll just type in Opamp, press Enter, and then place it on the schematic like so. You don't need to change any of the parameters shown here. The only parameter that is worthy of notice for our purposes is the output resistance of the opamp, R3, which is set currently to 100 ohms, and if you so wish, you can set this to 0 ohms to make the amplifier even more ideal. In this particular simulation, this won't matter a great deal. One thing you absolutely have to do is put a ground reference in, and that goes onto pin 5 right here. Pin 4 can remain unconnected, pin 1 is your inverting input, pin 2 is your non-inverting input, and pin 3 is your output. So we can simply move this whole gibberish here out of the way, so we can put some stuff around the amplifier. We want to put some resistors to create a feedback network, so press Ctrl L, type in RES, select the resistor in closed form, and then place it on the schematic like so. Then press Ctrl C and Ctrl V to create a copy of that resistor, and then simply connect them together as shown. Notice the IDs for these resistors, R1 and R2. Of course, I've placed them in this way so that they would automatically have the right numbers, but you can change the ID by simply double-clicking and typing in the name that you want to give it. Now we need to set up an input voltage. We simply press Ctrl L and select an ACVS element. This is an AC voltage source, which is just what we're looking for. And then we can simply add a ground reference at the bottom of it, and also connect it to the first resistor like so. We'll also need a load. We press Ctrl L again, get another resistor, and then we right click to rotate it and place it like so, have a ground reference at the bottom of it, and then connect it to the output. We can then change its ID to RL to make sure that we don't get confused, and then we can change the values. Of course, we want a high load resistance, so we can simply set this to 10K. You can type in 10,000 or simply 10 and the letter K, and you get the right thing there. The magnitude of the input voltage doesn't matter a great deal in this particular case. At the moment it is set to 1 volt. You can change it to whatever you like. I think 1 volt is a little bit too much. This is the amplitude, not the peak-to-peak amplitude, the peak amplitude. So how about we set this to something a lot smaller, and we can set it to 50 millivolts. And to type this in, just type 50 and then M. You can of course also type in something like 0.05 volts, and this would be exactly the same. So up to you how you do it. Now if we want a gain of 100, we simply have to make sure that the ratio between R2 and R1 is 100. And also we want to try and avoid having small resistances here, because otherwise the current at the output will flow down this network, and we don't want that. So let's choose resistors of the order of kilo ohms. Let's say that we make R1 1 kilo ohm, and then we make R2 100 kilo ohms. Now we have to add some measuring devices which will allow us to plot the input and output voltages. Simply press Ctrl L and then type in V_meter, and this gives us a voltage meter which we can place across our load resistance like so. And also we can simply click on it, press Ctrl C and Ctrl V, and place it across our input generator like so. We can change the ID of our V meters so as to avoid confusion. Let's call the first one V in, and then the second one here we'll call VL. Now, of course, there is one thing that we have not set. Look at our AC voltage source. We set the magnitude there, but we have no indication as to what frequency this is operating at. Well, the frequency is set globally. If you've seen the previous tutorials, you will know this. So you have to go to Project Options, double click, and then you've got the Frequencies tab where you can determine what frequency you want to use. In our case, we will be working at 1 kHz to start with. So we change the units to kilohertz down here, and then type in 1 here and select single point and then apply. Now you can see in the current range we have just 1 point. This corresponds to the frequency of 1 kilohertz. Then select the global units tab and then change the frequency units here to kilohertz and then click on OK. You can see that there is something missing here, and indeed there is. We have to connect our non-inverting terminal to ground. So we can simply get a ground from up here or press Ctrl G and then connect the non-inverting terminal to ground like so. Now we can simply go on to graphs, right click on graphs, create a new graph. It'll be a rectangular graph and we'll call this V-in and V-out, and we'll simply want to display the time waveforms of the input and output voltages. To do so, right click on the graph, select Add a new measurement, and then on the measurement type go to nonlinear and then select voltage and V-time, since we want the time domain waveform for our voltage. We then have to select the data source name. In this case we've only got one schematic, so this is where it will be coming from. And then we have to say which measurement component we want to get the time domain voltage from. Just click on the 3 dots, your schematic appears, and then you can simply select the component which you want to use to measure the voltage. So we want to use the voltage meter at the input. Click on that, click on OK, and apply. Then we want to add another measurement for the output. So again, click on the 3 dots, and then click on the voltage meter at the output, and then on OK, and then apply. And you can see here on the legend in the background, we can already see our measurements appearing. Click on OK, and then click on the Thunderbolt to simulate. You can see here that we've got our V-in and V-out, which are very, very different in amplitude. So it's very difficult to see them. You know from previous tutorials that what you can do in this case is right-click, go on to Properties, and then you can simply select the Measurements tab, and you can associate each measurement with a different vertical axis. So we can, for example, keep the input voltage on the left axis, but then we can click on the load voltage and then associate it with the right axis, like so. Then click on Apply and OK. And now you can see the input and output voltages a lot more clearly. We can reduce the size of the legend so we can see things a bit better. Notice that in the legend it tells you which axis refers to which measurement. So for example, for the V-in measurement, we are using the left axis. So the blue curve here, the scale that you have to look at is the one on the left-hand side. And then for the load voltage, we are using the right axis. So you have to look at the right-hand vertical axis to get the actual amplitude of the pink curve. We can see that we have an inverting amplifier, since the input and output are 180 degrees out of phase with one another, and we can also see what amplification we get. Simply right-click on the graph and select Add Marker, and then click on the blue curve, and then again right-click, select Add Marker, and click on the pink curve. Then right-click on the marker and select Marker to Max, and then right-click on the other marker and select again Marker to Max. And you can see that the amplitude of the output voltage is 5 volts, the amplitude of the input voltage is 50 millivolts as expected, and hence we're getting a gain of 100. Now let's look at what happens when we use a real amplifier. First of all, we have to import the model for a real amplifier, and we've seen this in previous tutorials. The file is available on Blackboard, and it is the model for the LM741, which is the amplifier that you will be using in the lab. In order to import the model, you have to right-click on Netlists on the Project tab, and then select Import Netlist. Then simply select the file that you want to import, and then click on Open. Now this has been imported into the AWR design environment, and hence we can use it for our simulation. In order to use it, first of all, let's go back to Circuit Schematics, right-click on Circuit Schematics, select New Schematic, and we'll just call it Real Inverting. And then, in this case, we won't press Ctrl L, we either press Ctrl K to select the sub-circuit that you see here, the circuit that we've imported, or simply click on the sub icon up here, and a list of the sub-circuits available will be displayed. In this case there's only one subcircuit, so we'll just double click on that and place it on the schematic like so. As you can see at the moment, with this box with 5 pins, it's not really clear what is what. So we simply right click on it and select Properties, and then select the Symbol tab and scroll down until we find a symbol called Opamp. You can select either Opamp 51 or Opamp 5, it doesn't really matter, and then click on OK. And you can see now that it is a lot clearer what each pin does. Of course, this is the inverting input, this is the non-inverting input, and this is the output. These two are a little bit trickier. They are the power supply terminals, of course. The one closest to the inverting input is actually the positive power supply, and the one closest to the non-inverting input is actually the negative terminal of the power supply. Once we know that, it should be no issue at all. So the first thing we have to do in this case is actually supply some DC power to our device. We can do this in a number of ways. I will do it in the simplest, most intuitive way possible. Simply find a DC voltage source by pressing Ctrl L, typing in DC VS, and then placing a voltage source like so. Remember that you right click to rotate. And then of course you have to also add a ground reference for it. We'll select the value of this voltage source to be 15 volts. And then we'll connect it to the positive terminal of the power supply. Then we can simply press Ctrl C, Ctrl V, and again put another power supply down here. And of course we have to set its value to minus 15 volts because this is the negative power supply, and we connect it to the relevant terminal. And then of course we can press Ctrl G to add a ground terminal right there. Now our op-amp is completely powered up, so we are ready to do something with it. To zoom in and out, you can simply keep the Control key pressed and then use the scroll wheel of the mouse. And this will give you a little bit more space. But of course you can also use all the stuff up here to zoom in and out. Now we have to place a resistive network around our op-amp as we did earlier. Press Ctrl L, type in RES, and then place your R1 right here, and then press Ctrl C and Ctrl V and place your feedback resistor R2 up here. Now you just connect them as before. Now of course we have to connect the non-inverting terminal to ground. We need to have this terminal grounded. And now what we can do is again change the values of the resistance to the same values as we had in the previous case. So we can change this to 1 kilo ohm and then this one up here to 100 kilo ohms. Again, we need to have an AC voltage source, so we can simply press Ctrl L and type in AC VS and then place it at the input like so, have a ground reference at the bottom of it, and connect it to the resistor R1. We'll set the magnitude of this to the same as we did before, which was 0.05 volts or 50 millivolts. Then we'll have to have a load resistance, and yet again we can simply press Ctrl C and Ctrl V and then rotate it by right clicking and placing it at the output like that. And again we'll set this to 10 kilo ohms as we did before. And then we'll add a ground connection at the bottom of it. Okay, we're all set to go. We've got the plus 15 up here, the minus 15 down here, which is something we didn't need for the ideal amplifier. The non-inverted terminal is grounded. The inverted terminal has got the feedback network connected to it. We've got a load resistors and we've got our signal generator set up. Of course, the frequency at which this operates is again the same that we set in the project options on the frequency tab. Now, of course, the only elements missing are measuring elements, and again we'll need some voltage meter. Press Ctrl L, type in V_meter, and then place one on this side and connect it to the input voltage, and then press Ctrl C and Ctrl V and put another one on the other side and connect it across the load resistor. Then we'll change the IDs so we make them easily identifiable. We call this VIN, and then we'll call this one here VL. Now right click on graphs, select new graph. This time we'll call this VIN and VOUT real, and we right click on the graph, select add a new measurement, and then we already have the right measurement selected here, which is VTime under the nonlinear tab. We need to select a different schematic however, and we'll select real inverting, and then we click on the three dots to select which element we want to measure from. So we'll select the voltage meter across the input voltage first, click on OK, and then apply. And then we'll go back and select the voltage meter across the load resistor, click on OK, and then apply. And then click on OK and simulate. Again, we have a similar problem as we did before, so we simply right-click on the graph, go on to Properties, and we've got the input voltage associated with the left axis, the output voltage also associated with the left axis, but we simply click on Right, and then we'll be able to associate it with the right-hand axis. Click on Apply, and then OK. Again, notice how the legend always tells you which measurement is associated with which axis. We can make this a little bit smaller to see things a little bit better. And you can see that we have a similar situation as we did before. There is, however, a little difference, and we'll see this in a moment. Press Ctrl M and put your marker on one of the voltages, and then press Ctrl M again and put the marker on the other voltage waveform. Then right-click on each marker and select Marker to Max. And you can see that in this case, what you seem to have is a greater voltage gain than you had previously. Don't be fooled, because actually what's happening here is that you have an offset. So if you look at the top and bottom of the waveform, you can see that the waveform is not entirely centered across 0. In fact, we can put a marker down here, Ctrl M, and then click on the waveform, and then say Marker to Min, and you can see that the minimum voltage of the waveform is different from the maximum voltage of the waveform. So there is definitely a DC voltage offset which you're seeing at the output, and of course this is not present at the input. Now you can make this your reference marker to see what the peak-to-peak amplitude is. So right click and then select reference marker, and you can see that the actual voltage here is 9.94, and hence your gain is a little bit less than 100. And you can clearly see one of the non-ideal aspects of the real amplifier, and that is an offset voltage at the output. Let us also look at another major difference between an ideal and a non-ideal amplifier. If we go back to our ideal amplifier and then we change the amplitude of our voltage to 300 millivolts, so 0.3 volts, then we simulate and we take a look at the input and output. You simply see that they've gone up by whatever factor, and this has not affected the amplifier operation at all. If we now go to the real amplifier and we set the magnitude to 0.3 volts and then simulate and have a look at the output, you can see that things are not quite the same. So the output voltage in this case is limited in its range, and in fact if you look at the delta between the bottom and the top, which is 27.88 volts, you can see that the actual maximum voltage swing which is allowed for a real amplifier is a couple of volts below the voltage rails. So the voltage rails have a range of 30 volts from top to bottom, and actually our waveform won't be able to reach 30 volts, it will be able to reach 27.9 maximum. How do we find out what the maximum input voltage is that we can have without distortion? Well, it's very simple in Microwave Office. We go back to our schematic for the real inverting amplifier. We simply click on the Tune tool and then click on the magnitude of our voltage source. This turns blue, and this means that we can tune it. So let's open again the graph which shows V in and V out, and also open the tuner. Now you can see that the tuner allows us to change the amplitude of our input voltage and to see the change in real time. So of course we have to lower it, because of course our gain at the moment is saturating the amplifier. It's taking us to a point where the voltage rails can't supply enough voltage for our output. So we simply have to lower the input voltage, and as we do so, you can see that the input voltage becomes smaller, but also the output voltage is coming back to a nice waveform. And now we've hit the bottom boundary here that is set by the tuner. We can change this, say we change it to 0.05, and we can continue to slide down until we become sinusoidal. So you can see if I go back up, there is a point where I start hitting the rails, and if I lower it down carefully, this is probably the point where I can still have a sinusoidal voltage in output without distortion, and this point happens to be about 50 millivolts, which is what we started with.